So in this session, we have three papers. The first paper is by Ms. Geetha, experimenting integration of custom ECDSA algorithm in OpenSSL. Ms. Geetha, please.
Good afternoon to anyone all present here. So I'm here to present a paper which is titled Experimenting Integration of Custom Implementation of ECDSA Algorithm in OpenSSL, which is co-authored by Ms. Akila from SETS Chennai, and it is mentored as a part of UBS project by Dr. T.R. Reshmi, scientist and a principal investigator for UBF at SETS Chennai. It's not working actually. Yeah. So the overview of presentation goes like this. So introduction to the OpenSSL, an open source software library, crypto library, and review on attacks that has happened inside the OpenSSL crypto implementation. So the methodology by which we can add a custom implementations of any asymmetric or symmetric algorithms into OpenSSL. So which prescribes three methodologies through OpenSSL libraries, engines, and service providers. Recommendations for custom crypto additions based upon the applications, followed by conclusions and references that has been used for this presentation. So we would like to start with an introduction of an OpenSSL. So the OpenSSL is one of the most widely used cryptographic library for establishing secure communication over a TLS protocol. Almost all of the TLS communications, HTTP and web servers today in an internet world use an OpenSSL. So an attacking OpenSSL cryptographic implementation, of course, may take the web server or an internet environment by storm. So it is also, the OpenSSL also plays a vital or key role with cryptographic interface for secure key storage solutions like HSMs, facilitating the cryptographic operations inside those storage devices like tokens, hardware security modules, or smart cards, etc. In this regard, there is a growing need to customize the OpenSSL cryptographic modules for two main reasons that we have identified. One is to mitigate the known vulnerabilities that exist in OpenSSL implementation. By the next slide, we will be showcasing the prominent attacks that has happened on the OpenSSL crypto implementation. The second is to integrate the custom cryptographic solutions into applications like blockchain, where we have our own ECDSA implementations that will generate the key pairs, but take the X.509 certificate and other attribute-based certificates CSR, if we can able to use the OpenSSL implementations. So in this regard, this article explores the methods for adding custom cryptographic implementations into OpenSSL library, and also discusses the advantages and the disadvantages, the overhead that we are going to encounter by doing this. So this presents the prominent literature review on attacks that has happened on an OpenSSL crypto implementations. We have given only the 4 attacks, each for one algorithm, whether it is maybe a symmetric or an asymmetric algorithm. So first, it is a cold boot attack that happened on an AES 128 implementation of an OpenSSL in OpenSSL version 1.1. The nature of an attack, so by AES, there was multiple round operations. Of course, we know that. And to just reduce the overhead and improve the efficiency, it is a model to just pre-compute the round keys for an AES operation, store it in a consecutive address space of the memory, and then you can able to use it for your round level operations. So the nature of an attack is to retrieve the pre-computed AES round keys from the memory dumps. And it is successful in retrieving 11 disordered 128-bit AES round keys in an OpenSSL version 1.1, and 60% has been assembled to form a proper round keys. The second is an RSA and patch bleed attack that happened on an RSA implementation, on a 1024-bit RSA implementation of OpenSSL version 1.0.2f. So based upon the timing access of a level 1 cache, that is so RSA as a modular exponentiation operation. The exponentiation is a high power consuming operation. So based upon the level 1 cache access, it retrieves about 60% of a 1024-bit key in an RSA. And the second is an SCPD attack, that is singular curve point decompression attack that happened on an ECDSA. So attempt to know the SCPD curve point, base point variant before a scalar multiplication, thus leaking a secret value. So fetches the 5-8 key from 140 signatures. So it happened in a version OpenSSL 1.1. And the fault injection attack that happened, is it a basic side channel attack that happens in ECDSA implementation, retrieves the secret key from the minimum number of signature, ECDSA signature, that is 4 signatures. That is also happened in a OpenSSL version 1.1. And of course, there are known vulnerabilities like heartbeat vulnerability that exist in an OpenSSL implementation. Yet it is one of the most widely used software library. It is an open source software library. So we have freedom to customize the open source software library based upon our need. So that is our point of discussion. So this is an architecture, OpenSSL inspired architecture from an OpenSSL documentation. So we just identify 3 places where we can add a custom crypto implementation into an OpenSSL. So one is the common services or the lib crypto modules, which is again the regular crypto operation for a crypto modules inside an OpenSSL will be hosted in the lib crypto module under a common services section. The second one is the legacy APIs, an application programming interface, which normal publicly crypto standards, PKI standards will be using to interface their engines into the OpenSSL. And the third is, which is supported by OpenSSL version 3 which is a third-party service provider API, which is hosted for vendor-based crypto algorithms. Like OQ is one of the most commonly used post-quantum service provider that uses a third-party service provider for an OpenSSL implementation. So in this regard, we have summarized 3 methodologies by which a crypto implementation can be added into an OpenSSL. So first one is addition of new crypto algorithm into lib crypto module of an OpenSSL, creating a new engine which is similar to a PKCS 11 engine for an OpenSSL with custom crypto implementations, defining a service provider library with a set of custom implementation and interfacing the library, third-party library with an OpenSSL. So we here discuss the steps with which we can able to accommodate or incorporate these custom crypto implementations by these frameworks. So the first one is 3 OpenSSL libraries. So the addition of custom ECDSA implementation, which is written in a C language, into the inbuilt crypto folder of an OpenSSL. So there is a language dependency. So because the OpenSSL crypto modules or crypto implementations comes with a structure which is called as an EVP, which is called as an envelope structure. So the structure must be strictly followed in order to incorporate your custom crypto implementations. So the source files, which is written in a C language, must be added into the crypto folder. So you have to follow the EVP interface for integration. That is, your algorithm and the code must be in a structure of an EVP. And you have to create an object identifier, the crypto module object identifiers. You have to map all the utilities like error collection, error creation, error collection, etc. For an asymmetric algorithm, since it is also works on a TLS layer, so you have to configure a TLS settings and you have to go for build info. The next is your OpenSSL engine. OpenSSL engine is a modular framework that enables the integration of various custom crypto implementations for hardware security modules or an alternative software algorithms to an OpenSSL library. So the public key crypto standard, crypto key version 11 is one of the mostly used OpenSSL engine for module integration of secure key storage options with an OpenSSL. So the implementation of custom ECDSA based engine in OpenSSL requires an engine structure that has been defined as the right hand part of a slide. So this is a structure with which you have to define your engine, test your implementation, compile it and load it, and you can able to interface it or call it from an OpenSSL. And the last part is a service provider to an OpenSSL. So as we already mentioned, the OpenSSL version 3 and higher versions host a provider API, that is a third-party provider API, to which a custom cryptographic implementations can be incorporated into an OpenSSL. So the detailed workflow or a pseudocode for this implementation has been submitted as an annexure or supplementary material along with our proceedings. So the provider holds a set of cryptographic implementation and it has been initialized by a provider.c file to the OpenSSL. So the custom algorithm will be implemented and will be attached as a calls to the providers. And a make file will be returned. A make file will contain information, the necessary information about the object identifier of an algorithm, the structure of the key, the time taken for the key generation, signing and verification phases, and of course the error collection, error codes. Everything will be written and the make file will be called by means of the test application. So you can able to see when you are able to interface an OQS service provider to the OpenSSL, it comes with a OQS crypto implementations and OQS will supply you the PQC implementation along with the structure of the key, the size, and of course the time taken to generate the key and the average time and the error code. Everything will be supplied by the OQS, third-party service provider. The OpenSSL command line will directly call as it is an implementation of an crypto implementation through the service provider algorithms. So these are the three methods with which we can able to add a custom crypto implementation into an OpenSSL. But we have, as we have tested all the three implementations, and we are going with adding a custom crypto implementation inside the lib crypto module of an OpenSSL for our application. We have some recommendations in this regard. So the first one is the engine or a service provider may be lightweight, may be easy to host it. While using a separate engine for a service provider with OpenSSL will reduce your overhead. But it is important to know that your crypto implementation will no more be secure. It will reside outside your OpenSSL software implementation. So the external placement of a crypto modules could introduce security vulnerabilities, making them more susceptible to attacks. And some applications like hardware security modules, which interact with OpenSSL through built-in interfaces like PKCS11, may not be aware of an additional external interfaces or engines that is hosted inside an OpenSSL. So this lack of awareness for HSMs or smart cards or any other storage options may create a compatibility issues and reduce the security. So in accordance with the specific environments, the engine and service provider approach are recommended primarily for environments where OpenSSL crypto implementations can operate independently without requiring a direct application interface. But with this, for our implementation, so we are hosting a CA for a blockchain, and with the secure key storage management system for a CA is accommodated by means of an SSM or a HSM. We have a custom implementation of an ECDSA inside our CA. So we are already a PKCS11 interface has been enabled for a HSM or an SSM module. So we just avoided an option of promoting one more engine above a PKCS11 or below the PKCS11 engine. And we don't want a third-party provider interface, since it may again overload your certificate authority. So we thought of we could directly implement or add a custom implementation of ECDSA inside a libcrypto module of OpenSSL. So the article highlights the need for custom cryptographic implementation in applications such as permissioned blockchain and hardware security modules. Embedding a custom cryptographic library directly into OpenSSL is identified as a practical solution for these types of applications. So OpenSSL version 1 supports the integration of separate cryptographic modules into the libcrypto module, allowing significant modifications into the EVP structures for symmetric algorithms and OSSL structure for asymmetric algorithms. The method, while potentially increase code overhead, enables the addition of cryptographic modules that meets the FIPS standards. It also addresses traditional security vulnerabilities present in other approaches and offers the improved timing efficiency. The choice of integration and the OpenSSL version should be guided by specific needs of an application, balancing security, performance, and feasibility for your application. So these are the references that have been used in this context, and that's it. Thank you. Queries?
Person will take workshop 2 questions. Any questions?
Sir? So it is P256, sir. Prime curve 256.
Any other question?
Thank you.